Alright, so this video is about simplifying complex rational expressions. So we best figure out what a complex rational expression is. So the definition is a rational expression that contains rational expressions within its denominator or its numerator, or both. Okay, so like these are just big fractions within fractions. So there's two different ways to think about simplifying these complex rational expressions. And the first one is the idea that you're allowed to multiply any expression by a form of 1 and use that to create a simplified version of the same expression. So let's take a look at this complex rational expression. This is a real simple one for our first example, so you can kind of follow along a little bit easier. Most of these are going to be involved with variables, but the idea is the same. So we're going to identify this as our numerator and this is our denominator, and as long as we multiply the numerator and denominator by the same number, we're not really changing the important information, and that's why this is called multiplying by 1. Anything over itself is equivalent to 1. So what we're going to do is look at all the denominators, and we're going to come up with a least common denominator, or maybe even a better way to say it is a least common multiple, and that's what we're going to multiply numerator and denominator by. And so if you take a second and think, what do all of these denominators, what would they all go into? You would say 24. So let's multiply the top, the numerator, and the denominator by 24 and see what happens. Now remember, we have to distribute, and both of these 24s are really 24 over 1, so we're only multiplying kind of like the numerators and then simplifying, but I'm going to do that by kind of simplifying first, and I'll kind of write it out so you can see what I mean by that. So, you could think 24 times 2 is 48 and then divide that by 3. But, an easier way to do that is say, well, 3 goes into 24 8 times. So really, this is going to be 2 times 8 plus, and now we're going to move to the second term up here. 8 goes into 24 3 times, so it's going to be really 7 times 3. And that's our new numerator. And now we move down here to the denominator. And again, you could just say 1 times 24 is 24 divided by 4 is 6. But again, I think it's easier in the long run to just say, well, 4 goes into 24 6 times. And so we're going to do 1 times 6 minus, and now we're going to have 6 going into 24 4 times, and have 5 times 4. Now it's a pretty simple process from here. You're just doing your order of operations. So we'll get 16 plus 21 over 6 minus 20. That will give us 37 over negative 14. And you always want to check to see if you have reduced what you're left with, if it's reduced far enough, and nothing else will go into both 37 and 14, and so there's our answer. Here's our next example, and you notice that we're dealing with variables now, but the idea is still the same. We're going to come up with a number, in this case variables, that when we multiply both the numerator and denominator of our rational expression, we'll be able to simplify it down. And you're still thinking of the least common multiple, and that means what does all of these go into? Okay, and we want to take the smallest thing that they all go into, and when you're doing that, you're looking for the biggest exponents of each of the variables. So in this case, we'd want to multiply both top and bottom by a cubed b squared. And we're going to go through the same process. I'll write this one out just so you can see what's going on maybe a little bit better. But when we do this, the numerator will become a cubed b squared over a cubed b plus a cubed b squared over b. Now we're moving down into the denominator, and we'd have a cubed b squared over a squared b squared minus a cubed b squared over b squared. And now I'm going to simplify all of these down. Now in the long run, you really don't need to do this step because you can cancel as you go once you get comfortable with what you're looking at. And I'm just doing this for the purposes of explanation here. But we're going to take this first rational expression in the numerator and simplify it down, right? The a cubes cancel, and we're left with a b plus, we move to the second one here, and this is going to be a cubed, and then one of our b's will cancel. So then we have a cubed b, and that's going to be over, going through the same process, an a minus a cubed. Now, just like when we did the previous example, you want to be able to simplify these down as far as possible. So now you're going to have to do some factoring. And you notice that both of these terms in the numerator have a b in common. So we're going to just take that out front and be left with a 1 plus a cubed. And we're going to take an a out of the denominator and be left with 1 minus a squared. And now we have to check to see if we can simplify any further. And you should notice that the denominator has a difference of squares in it, and the numerator has a difference of cubes in it. So we can actually simplify this a little bit further. And that would look like this. Okay, and you do have to remember all of your factoring skills. And we're looking through and seeing if there's any common factors that we can cancel. And there are. We have this 1 plus a and this 1 plus a. And so our most simplified version would be b times 1 minus a plus a squared over a times 1 minus a. Alright, so here's all the steps that we did, and they're just written out. I know a lot of people like having the steps to look at as they go. First one is to find the LCD, and remember that stands for the least common denominator of each part of the overall rational expression. And that's what you're going to use to multiply top and bottom by, which is like multiplying by 1. Make sure that you distribute it to every term in the original complex rational numerator and denominator. Once you do that, you're going to simplify it by adding everything we can together. We're going to factor things out and see if we can simplify further. Okay, so this will be the last example that I do by the first method, and it's all the same steps as the first two examples, but I will say that when you're coming up with your least common denominator, you really want to factor anything that you can first, because that'll give you a better idea of what you want to use as that least common denominator. So I'm going to start off by doing that, and we're going to have a 2 that we can take out of this first part, and be left with x minus 1. And this is going to be the difference of squares, so that's going to factor into x plus 1 and x minus 1. And now we're going to look through and see what we need to use as our least common denominator. And basically, if you see a factor, a different factor in any of the denominators in this complex rational expression, that has to be part of what we're going to use. So we have to multiply both top and bottom by a 2, an x minus 1, and an x plus 1. Okay, and all of these are repeats, so we don't have to look for any others. And so that's what we're going to use. And you're welcome when you do this distributing step. And remember, you have to distribute to everything. You can write it all out and then do your canceling. But in the long run, I think it's going to be easier for you to do your canceling first. And I'm going to do it here just so I can save some room down here. But when you're looking through, this 2 will cancel with this 2, and this x minus 1 will cancel with this x minus 1. So we're left with 3 times x plus 1. Make sure you're using your parentheses because we will have to distribute later. Minus, and again, what are we going to be left with? Well, this is only going to cancel the x plus 1s, so we're going to be left with a 2 times x minus 1. Now we're moving down into the denominator and looking at the same type of things here. So this x minus 1 will cancel with this x minus 1, and so we're left with 2 times x plus 1 plus 2 sets will cancel here, the x plus 1s and the x minus 1s. So we're left with just a 2x. Now, like I said a second ago, we're going to distribute everything we can and combine like terms to see how much further we can get this simplified. So this is going to be 3x plus 3 minus 2x plus 2 over 2x plus 2 plus 2x. Now we're going to combine like terms. In the numerator, we're going to have 3x minus 2x, so it'll be x plus 5 over 4x plus 2. And you should always keep checking, so we can factor a 2 out of the denominator. But we're not left with anything that will cancel. These factors aren't the same. So really, in this case, this answer is fine. Maybe this answer is a little bit better, but either one is pretty acceptable. So here's the second method that you can use. And in this method, you're kind of treating these complex rational expressions as 3 separate problems. We're going to combine the numerator into its simplest form, and then we're going to combine the denominator into its simplest form, and then we're going to divide the two. Okay, and so these are all fraction rules that you should still remember. So what we're doing here is that we're going to find a common denominator of the numerator. Okay, and so that's going to be a 20. So then I'm going to multiply the first fraction by 4 over 4, and get 8 over 20. And the second fraction by 5 over 5, and get 15 over 20. All right, now I'm going to move down into the denominator and do the same thing. Get a common denominator between 9 and 8. That would be 72. So I'm going to multiply the first fraction, numerator and denominator, by 8, and get 8 over 72, plus multiply by 9 and get 27 over 72. And now I'm going to combine these fractions. And so we're going to have a negative 7 over 20 in our numerator, and then we're going to get a 35 over 72. Now we have a fraction divided by a fraction, and our rules say that we flip the second fraction and multiply them together. So we would have negative 7 over 20 times 72 over 35. And now we want to simplify as far as possible. And you're welcome to multiply straight across and then think of a number that will go into both. But I think it's easier to simplify beforehand. And so a 7 will cancel with the 35. And you'll have a 5 in the denominator here. A 4 will go into 20 and 72. So when you divide by 4, you'd have another 5 here. And then an 18. And now we're going to be as simplified as possible when we multiply these together. Don't forget about your negative sign if you have one. And so this is going to give us a negative 18 over 25. So we're going to use these same ideas, and we're just going to start putting in variables and expressions and simplify from there. Okay, so now we have some variables involved, but again, we're just treating this like 3 separate problems. We're going to subtract these 2 rational expressions. Let's do that first. So our common denominator up here would be an x squared. So we're going to have to multiply this first fraction by x over x. And that would give us 3x over x squared minus 2 over x squared. And I'm going to just finish this part off since we're kind of treating them as 3 separate problems. That's going to give us 3x minus 2 over x squared. Now let's go down to the denominator here. And our common denominator in this case is going to be x squared times x minus 2. And that means we're going to multiply this first fraction by x squared and have 3x squared over x squared times x minus 2. And we're going to have to multiply the second fraction by x minus 2. So we would have x minus 2 over x squared times x minus 2. And that'll simplify into 3x squared plus x minus 2 all over x squared times x minus 2. So what we're going to do now is we have this fraction divided by another fraction, so we're going to flip the second fraction and multiply. And so we would have 3x minus 2 over x squared times x squared times x minus 2 over 3x squared plus x minus 2. Now we're looking for factors to cancel, so we better start off and see if we can actually factor this part, and we can. So I'm going to rewrite this all as 3x minus 2 over x squared times x minus 2 over 3x minus 2 times x plus 1. And now we're going to go ahead and cancel now. And we can cancel our x squareds. We can cancel a 3x minus 2. And that's all we have that we are able to cancel. But we have it way simplified down. We just have an x minus 2 over x plus 1. Okay, so here's the steps listed out for you. And you're just treating this like three separate problems, right? Add or subtract the numerator together, add or subtract the denominator together. Once you have one fraction divided by one fraction, you flip the second fraction and multiply. You may have to factor again, and then cancel any factors that you can find in the numerator and denominator. So here's the last example that I'll do, and we're going to do it by the second method, and we're going to add the two terms in the numerator together. So we need a common denominator, and that'll be x. So I'll multiply the 1 by x over x. And so we'd have x over x plus 2 over x. We will add the two terms in the denominator together, and the common denominator down there will be x squared. So I'll multiply the 1 by x squared over x squared. So that will look like this. We're adding the numerators, so we have x plus 2 over x, and x squared minus 4 over x squared. Now we have one fraction divided by another fraction, so we need to flip the second one and multiply. Okay, and I'm going to cancel any like factors now, and that means that I'm going to need to factor this. This is the difference of squares. So this will be x squared times x plus 2 over x times x plus 2 times x minus 2. And now I'm going to cancel the x plus 2's. I'm going to cancel one of the x's, and our final answer will be x over x minus 2. Now you can choose either of the methods. Okay, they are both equally as effective. I suppose some problems probably set up easier for one method or the other, but essentially you're doing the same thing no matter which method you try. So find one that you're comfortable with and go from there.